So in this question, we're asked to solve for the general solution to the differential equation, and then as a second step, find the unique solution, and we have to do that using the condition. So looking here, we've got as a first bit, the differential equation we're going to try and solve, and then the second part here is the condition, which we'll use near the end. I've popped here the steps that we're going to follow through. You should be able to use these steps anytime you want to solve a differential equation using the separation technique, which is what we're doing today. So to start off with, I'm just going to carry down my differential equation, and we're going to try and separate across the equal sign, as you can see here, the different variables. So our variables that need separating are the x's and the y's. Something like a 5 is a constant, so it doesn't matter what side that ends up on. It's just, the x's and the y's that needed to be separated across the equal sign. So as a first step, what I might do is bring the y to the other side of the equation. So that means it's going to become 1 on y, dy on dx, is equal to negative 5x. And then as a second step, I'm going to move this dx that we have up to the right-hand side, and then that should be pretty much it in terms of achieving separation. Okay, so what we can see is that all the y's are on the left and all the x's are on the right. Again, where the 5 goes, it doesn't really matter. I'm just going to leave it on the right though. So now that we've done that, we should be able to move on to the next step, which is to integrate our equation and find the general solution. So the general solution to this equation is going to be whatever the subject is on the top. So that's y. And we want to have it isolated in terms of, in our case, x's on the other side. So if I integrate here, the integral of 1 on y, this is saying with respect to y, that goes to the natural log of y. And here when we integrate, we use our power rule, so we add 1 to the power, so this has a little implied 1. So 1 plus 1 goes to 2, divide by the new power, which is 2. And because we've done indefinite integration here, we need to have our little plus c. Now, if you wanted to, you could have a plus c for each integration. However, what you're going to find is that they're going to end up compacting back together anyway at some point, so you only need to carry 1 through. So that's why I've popped it just 1 in our equation, and I'm going to choose to put it on the right-hand side, but equally it could go on the left. So I can make this a little bit nicer for us. It would go to negative 2.5x squared plus c, and we've still got our natural log on the left. Now, to get the y out of the natural log, what we need to think about is how we can do our power rules. And one of them is if you do e to the power of a natural log, essentially these cancel out with each other, and you're left with just whatever's in the bracket. So we're going to get y on its own, which is good, that's what we're looking for. But we need to make sure that we do whatever to the left, whatever we do to the left, needs to happen to the right. So we've done e to the power of the left here, it needs to be e to the power of the right as well. So that means we're left with this here, and that's a perfectly valid general solution to our differential equation. However, there is a little bit of a trick that we can employ to make it a bit nicer. So what we've got up here is a little c, and what we can do is actually get our little c, or our constant, out of the power. So there is a rule where if you have the same base on your equation, and what you can do then is pop your powers together and they actually add. So here we've got our kind of right hand side happening where we've got an addition in our power. What we're going to try and do is move back and separate them with the two bases. So we'll get 2.5x squared multiplied by, again, the same base, e to the c. And what this means is, e is just a number, it's like 2.71 with a lot of decimal places on the end, and c is just a number as well. So rather than writing it as e to the c, I'm going to introduce a new constant, which is called a, and it's just going to kind of combine them together. So rather than writing e to the c, we can write something that's a bit cleaner, which is a. So we're going to get e to the negative 2.5x squared multiplied by a, or we can write that even neater again with the a out the front. So this here is the nice version of my general solution. Okay, but just remember that other one that we came to before, that had the c up the top, that is perfectly valid as well. Alright, so we'll move on to the next little bit, which was now looking for the unique solution given the condition that we've got. So that's step 3 here. We're going to use our condition in order to obtain the constant in the general solution. So we've got y of 0.4 is equal to 10. So let me just pop that here. So what this is telling us is that this is saying y is a function of whatever it is, so x here. So at x is equal to 0.4, we've got that y is equal to 10. So we can substitute this information into our general solution, and we should be able to find out what a is. So we'll get 10 is equal to ae to the negative 2.5 times 0.4 squared. So this here simplifies to just be e to the power of negative 0.4, which is a bit nicer. And then if I want a on my own, all I need to do is divide by the e to the negative 0.4. And if I type that into a calculator, it comes to approximately 14.92. So that there is my constant. And the last step, as we've got up here, is that we just want to sub the constants into the general solution, and that provides us with the unique solution. So if we jump down here, I'm going to pop the 14.92 up here for a. And that there then becomes the unique solution to my differential equation. So it's a solution to the differential equation that also meets the condition that y is 10 when x is 0.4. So that's all there is.